We live? Oh, right. Okay. Thank you guys. It's a pleasure to start the second day of the M17 Conference. It's so nice to see all of you. And yeah, without further ado, I would like to present to you the first satellite topic of today. I had a great pleasure. It was quite some time ago, 2 years ago. I was at the European Space Agency working as an intern on the OPSAT mission. And I would like to talk to you a bit about what the mission was, how was it made, how was it built, and what are the unique features of the mission, and how does it involve the M17 protocol we've all come to hear about here. So, yeah. The OPSAT mission is a space laboratory created by the European Space Agency in the last decade, like since 2012 to 2015. They wanted to create a platform that would enable testing of new technologies for the space sector. So basically, over the years, the European Space Agency, or all space agencies and all space companies had a non-risk approach to technology. Yeah? So they would use technologies that they used before, they knew they were working, they used technologies that they had a deep understanding of, but that ended up being quite older technology. Yeah, flight proven, but perhaps not the latest in terms of specifications. Yeah, so that's why in 2019, since 2015 to 2019, they designed an OPSAT satellite, which was meant to test new technologies, provide a platform which would enable new contributors to test new solutions, and break the cycle of never flown, will never fly. Yeah? So we have technologies that never been to space, so we'll never use them. We're gonna fix it using this mission. So they provided a platform, a technical platform, which you could use in a non-bureaucratic process for free. You could propose an experiment based on the hardware provided, and you could just deploy it in space. Yeah. And each OPSAT had a theme. The first mission was meant to deal with communication protocols. So they included several hardware payloads dealing with radios, including a software-defined radio, which you could reprogram. So about the hardware. The entire satellite was split into two parts. The platform, which provided the sort of the base of the satellite, which we as the operators always had control over. Yeah. So if anything bad happened with the satellite, there was one known part of the satellite built quite conservatively, which would perhaps turn on and off again the satellite, and would put it in a known configuration. And then was the entirely experimental part, which just included all the toys, which there was no guarantee that they would work in the first place. Yeah, that included the satellite experimental processing platform, which was basically like a Linux compatible system on a chip board with an FPGA and a normal ARM CPU, not radiation hardened. And quite fast. It was called the fastest CPU at the time when sent to space. Yeah, the fastest computer ever on a satellite, and it's just 1 gigabyte of RAM and 800 megahertz of a core CPU core. Yeah, there was the software-defined radio. I just realized I didn't put any more information about it, but it was Flying Microsystems, also a commercial off-the-shelf standard, the SDR, which was the latest at the time. And they just put it in. The University of Graz in Austria was responsible for the design of the board that put it on the satellite. And there was some other experiments. A camera, of course, you have to take pictures, always nice. There was an optical receiver which you could use to it was really like a photon counter. So if you shine a laser on the satellite, you could actually see that there's light, the photons are approaching the satellite. So you can maybe not really do any communications with it, but you could, at least do a proof of concept of laser communications. And the ADCS system, which allowed you to maneuver the satellite, change its attitude, to point it in a given direction. It was especially useful for the X-band transmitter, high bandwidth transmitter, using it was it was in the X-band, in the 9 GHz range, which had a quite small slope of the antenna, of range of the antenna, so that needed quite precise pointing towards the ground to achieve the full bandwidth, and also useful for the camera. Yeah? So the pointing was useful for taking pictures with the camera. Yeah? So altogether closed up, it was a CubeSat. If I didn't mention it already, it was yay big, 30 by 10 by 10 centimeter, quite standard form factor for CubeSats, for satellites. And here is like the system layout of all the systems. Basically, the feature of the satellite was that everything was connected with everything using buses. There were like 3 different buses, and there was an FPGA on board the experimental computer, which could also take connections and like swap them over with the different components. So at the beginning, only the platform part was responsible for the mission. Yeah, but throughout the years, since 2019 up until the end of the mission in 2024. Like more and more responsibilities of the platform were shifted to the experimental computer. Yeah? More software was developed to reconnect, to fix the issues with the setup, and provide the operations from the experimental computer. Yeah, and it was launched in 2019 to sun-synchronous orbit, which means that it was flying over the dawn and dusk line of the Earth. So it was always the sun was always shining on the solar panels. The satellite had electricity most of the time, and it also meant that the flyovers over any given point on Earth were early in the morning, around 6 to 9, and late in the evening, around 1800 to 2100. Consequently, as I already mentioned, the satellite was launched in 2019. By the April 2024, it's sadly deorbited, so it's quite old information, but it's throughout the time, almost 5 years, it provided, it executed a lot of experiments which were quite useful. So on the ground side, that's how it looked in Darmstadt. This was my workplace for 6 months. This is the operational room at the SMILE laboratory in Darmstadt, and you have some racks with the corresponding equipment. So you have the satellite, which has all the systems in space, but you also have a copy of the systems on ground and corresponding systems which allow you to communicate, namely the antennas, corresponding with the bands and the radios, so UHF, S-band, and X-band. And we've also used satnav, which I will talk a bit more in a moment. Yeah, so for the S-band, we had a nice antenna ESOP1. This is like a parabolic dish inside. It supported operations of in S-band 256 kilobit per second up and 1 megabit down, which is quite nice. It covered most of the operations. And as I mentioned, the X-band, it wasn't really extensively used, but in tests you could see up to 15 megabits per second of downlink only capacity. I wanted to highlight this graph, which is a single graph from the perspective of the ground station as the satellite is flying over the Darmstadt, because the satellite had 2 S-band antennas, one gold one on this side and one on the opposing side. As you can see, when the satellite is flying over the ground station, you can see the handover between one of the patch antennas to the other patch antennas. So you have a high signal, then it dips to 0, and then you pick up the signal from the next patch antenna. So just so you get an idea of how the mechanics work of a satellite flying over the ground station. Yeah. The platform was using a UHF radio. Again, older, more conservative technology, which was known to work. The radio had quite a flight heritage, so it was something we knew that would work, and it was responsible for the basic commanding of the satellite. So not too high of a data rate, just 10 kilobits. It operated in ham radio range, and also it was compatible with the satnav stations, as I mentioned. So the European Space Agency opened up the software needed to decode the packets from the satellite, and we used it operationally at one of the antennas in Darmstadt. as you can see here, but also it was open up to the community, and everyone with a satellite stations could decode the code, the signals, and it was put on the satellite network, and we as the operators had a key which enabled us to decode the telemetry for operational use. So sometimes it happens that we couldn't establish the main S-band link, and we could rely on the ham radio community to help us find the satellite. So that was a really nice feature, and really nice for, I want to highlight, like, it is not usual for a space agency to open up their hardware, to open up the protocols, and it was really modern for the European Space Agency to do that. Last element of the ground segment is the flatsat, which is basically the copy of the satellite in a nice platform in which you can deploy the software before you deploy it on a real satellite, and just see if it works. Yeah, you can't really test it as if it was in space because the reaction wheel is not working, the camera is not really the same, but you can just see if it behaves the same way as it will do in space. Yeah. So from the perspective of me as an operator, you could connect. We had the antenna systems, and we had the sort of software systems. There was like that nice feature of OPSAT is that everything was virtualized. So there was one server room, one rack with all the equipment that you needed to connect to the satellite. It was running environment with the operational software, and you could connect using a laptop and just like a thin client, like a remote connection, and work with the satellite directly. Yeah? So more about the software, the operations, like that. What you can see every day is basically these 3 windows. And in order, on the bottom left, on the bottom right, you can see SCOS 2000. SCOS 2000 is software written, as you might guess, in the year 2000, which is like the base software to communicate with all spacecraft of the European Space Agency. And it was quite modern at the time, I'm sure. As you can see in the bottom right corner, you can see like a terminal window which shows the telemetry from the satellite as it's flowing. So basically like live data about the satellite, what is the energy levels, what are the given states of the components and such. And in other windows you can see the telemetry packets, so not the data but just the individual packets which update them. And you can also set packets to the satellite, basically predefined commands which are already established in the onboard software, and you can provide parameters and send the commands to the satellite. On the higher level of abstraction, written around the years 2010, is NATIS, which is quite a software which works on a higher analogy, so you can work on operations. So you have a operations library, repository, which has already predefined entire configurations you can enable on the satellite. So for example, turn on a camera, yeah, and it will run through a checklist. It will check the relevant telemetry coming from the satellite, and based on the conditions, it will send the appropriate commands. Yeah. So it also shows you the evolution of operations from the perspective of European Space Agency, in which originally you would have a paper procedure, you would follow along and just enable the right commands in this SCOS 2000. You would literally just click around and like send the commands live, or maybe prepare like a command stack which we would send right away, but you would prepare it manually. And in later missions, you could automate it using a programming language, basically. The procedures were written in a special script language. It also comes with the change of the characteristics of the ESA missions. So in the beginning, well, you had a sort of slow flying missions like interplanetary missions, like sun solar system missions, in which you had a communication window with the satellite, which can be counted in hours. So you have basically the entire workday to send the commands to a satellite, and then you need to wait like 20 minutes for confirmation of the commands. Yeah, so perhaps the slower pace was okay. But for quicker missions like low Earth orbit missions like OPSAT, you need to catch up. Yeah, like you have only 9-minute window of the satellite flying over your head. You better send all the commands. And so that's what was available at the beginning of the mission. But smart interns throughout the years of OPSAT created more modern software, Excel, in which you could create entire schedules, calendars. You could take the procedures and put them in an Excel sheet and tag them with timestamps at what time they should be executed in the future. And give it all the parameters, for example, to enable a given experiment at a given time, or reconfigure the spacecraft to appropriate state. I'm sure you could do it in the previous software, but the interns wrote an Excel sheet with all the scripts to make it easier. Yep. So yeah, and I wanted to touch up on one more thing. So basically, the meat of OPSAT was the community platform in which you could easily deploy your software on board. So basically, we had a pipeline in which you could connect with our operations center, basically a file server. You could drop in your source code for the experiment you wanted to run on the satellite. It will be automatically packaged into the right format. Of course, you would have to pre-compile it for the given architecture of the satellite, but then it would be pre-packaged for us as the operators, and then we could test it on the engineering model, see if it works okay, if it's turns on at all. And then using the connection with the satellite, with the S-band connection. One of the features of the S-band connection was that over the years of OPSAT, people implemented on the FPGA on board a direct connection between the S-band radio and the experimental computing platform. So basically, it was as if you had a direct Ethernet connection run all the way to the experimental computer, and we had a piece of software on ground called Automax, which would basically check if the satellite is flying above, but really it would look for an Ethernet port to be open on the Linux machine that was connected to the system. And if the port was online, that meant that the virtual Ethernet cable was connected all the way to the experimental platform, and it would have a direct SSH connection. But we could all use all kinds of Linux-based commands to communicate with the onboard platform. So throughout the 9 minutes as the satellite was flying over, we could drop in any experiments we wanted, and then when the satellite was out of sight, we could use all the above mentioned tools, previously mentioned tools, to enable the experiments at the right time and reconfigure the spacecraft if needed. Yeah, so that's basically the first 3 months of my internship, just trying to figure out how this entire system works. And over the next 3 months of my internship, I was focusing on the software-defined radio subsystem. So here I have a little bit more details about how it looked before and how it looked after I've done working with it. So basically, OPSAT was not all great. The experimental computer had some flaws, especially after 4 years in orbit. A lot of the compute power was lost, one of the CPU cores was not working, there was limited amount of RAM available, and on the contrary, the software-defined system, radio system, is quite data hungry. Yeah, it generates a lot of data. So basically, the software-defined radio was limited to around 16 seconds of recording, maybe 30 seconds of recording if you are smart about placing the files. And what I wanted to do in my work was to sort of route the data in such a way that it will circumvent all the limitations. So instead of writing directly to the file system, actually to the RAM, we would write directly to the eMMC memory, which was included on board. And actually, we used for that. I was really happy because at the time the Libre Space Foundation was contracted on OPSAT to work on the software-defined system to develop a piece of software, FPGA configuration, and a corresponding driver in the file system to enable longer time recordings on OPSAT. Yeah, so they wrote a piece of software which was basically doing most of the work, but what needed to be done from the operational perspective to configure it in such a way that it would be useful for the operators to work with. Yeah, so basically, if I have the next slide, it's like it was organized in such a way that the operator could give it a frequency, the SDR would tune to it, and it would write directly to the relevant memory, circumventing all the limitations of the system. So, big win for open source. A useful piece of software was written and could be changed to fix an operational issue. And yeah, I don't want to go too much into depth, but that's basically the topic of my master thesis. Yeah, so onwards to the M17 protocol. Perhaps there's not too much to tell about it, but when I first initially got to work with the software-defined radio system, I was like, okay, I better have a useful signal to hear from. Yeah, like I don't really know how you can hear stuff from space. So we did some initial recordings of like from space, flying over whatever part of the world it was at the time. But I don't know any useful signals, any useful references, yeah? So at the time I called up Wojtek, SP4EVA, and I was like, yeah, I've heard about this cool stuff, this cool thing which is M17. I'm actually curious what we can do with it, yeah? So we actually ended up having a, let's just see what works, yeah? Like let's just arrange a communication window, let's just send something to the satellite and see if it works, yeah? So we found quite a nice path directly over this place, like 90 degrees azimuth. The satellite was flying right over Warsaw and Nowy Dwór. And Wojtek with a TYT MP4EVA radio just transmitted. I believe it was also an Arrow 2 antenna. I calculated the link budget at the time for it, and we seemed to have enough link margin to just make it to the satellite, especially that it was short distance, yeah, directly upwards, so around 500 kilometers to go. And you can see the signal actually here, yeah? So this is the signal of M17. Maybe you can recognize the characteristics of the signal. But it's ended up not being enough to decode. I think the file is in the GitHub repository down there, so you can download the file. Maybe the tools are gotten better, I'm not sure. Perhaps 2 years it is possible to decode. Maybe you could use some extra trick. I've never actually learned what Wojtek told me over the radio, but I'm sure it was all great things. But yeah, also I think this was the next sort of stepping stone for me to work with the software-defined radio, because as you can see, that is not the only useful signal in the spectrum. Yeah, there is actually some ham radio guy that was just talking on I don't know, some repeater maybe, and you could barely hear what he says. Like also the link budget wasn't quite there to like decode the FM signal. But you can see like all of the different signals coming from Earth, and also some interference that was not obvious before to me. And I've actually never learned where it comes from, but there is a lot of horizontal sort of artifacts in the spectrum, perhaps coming from aliasing from some higher frequencies. Never really got too much into it. It never showed up on the ground system on the flat side on Earth. And we can't really check what was going on in space. Yeah. So this was the first recording, and this was also perhaps for some people in the audience, that was one of the later recordings during the Congress, House Communication Congress in Hamburg, and actually have some pictures of the communications. Me and my friends used one radio to communicate with voice. We sent some New Year's wishes, all the New Year's of 2023 to 2024. And actually, Libre Space Foundation was also transmitting, I believe here somewhere was an SSTV signal, but also the link budget wasn't there. I don't think it was ever decoded. But in this case, the radio communication, analog radio communication was barely recognizable, so it was a nice test. Yeah, and yeah, just to finish up on what my software package did on board, the part of the master thesis and my work on the software-defined radio subsystem. Basically, I just created a small script package, partly in Python and Bash and other tools, to like enable downsampling of the sample. So the observation from the M17 experiment was that you have all those different signals. Oh, I didn't mention why I was doing it in the first place. So basically, each SDR recording was like 100 megabytes. Thanks to the Space Foundation and their software, we enable longer recordings to the onboard memory, and in theory we could go all the way to gigabytes. Yeah, if we created a big enough partition in the memory on board, we could go way above 100 megabytes of recording time. So recording space, which would be like a minute, or with smaller bandwidths, like several minutes of recordings. Yeah. But then we have the limitation of the radio budget, the downlink budget of the S-band radio, which was used at the time mostly. Perhaps with the X-band radio it would be an issue about 15 megabits per second, but we mostly use the S-band radio just for convenience. And downloading just this one recording took like 3 days, like 6 to 9 different passes, So it just was not practical to work with the SDR subsystem. So I designed like 3 steps you could use to use the radio. First, you would record, as I described, 100 megabyte, 200 megabyte recording to memory on board the satellite. Then you would generate a waterfall plot, basically this image in black and white. It's a little bit simpler. And then the operator on board on ground could say, okay, from all the signals I see in the spectrum, probably this is the one I want. Yeah. I can hear it, but from the characteristic of the signal, I can tell that it's probably my signal, and I knew at which frequency I sent it, so I'm pretty sure this is the one in the spectrum. Yeah? And then the software would provide a downsampling action in which it would center the signal and then reject all of the signals, and the resultant file would be much smaller, in like 2, 3, 5 megabytes, and you could download it right away. So that basically sped up the work with the software-defined radio, but that's something that's the only 2 recordings I managed to do, the M17 protocol and then the mine recording from Hamburg. So that's pretty much it about the radio subsystems. I'm happy to talk more about how the specs of the radio looked, perhaps why we were not able to decode the M17 protocol. I'm open to discussion here. And I just wanted to finish up, as I said, the mission ended in April 2024, but it had a great track record. That was not the only experiments that were run on board. There was a chess game that was run on board. You could actually play chess with the satellite. We've also played Doom on the satellite. That's also a nice feature. I gave a talk actually last week about how did it work. It's basically the same presentation as here. I covered the way how you can deploy software. So one of the software packages on board was a compilation of Doom, in which the satellite would first take a picture. It would recompile the game with the picture of the Earth, or just the picture taken from the camera, into the texture of the sky, and it would play a demo of the game and capture a screenshot at the right time when the character was looking out of the window, and then you would get a result downloaded to Earth. So that's actually made by a guy called S.D.R. I highly recommend you finding out more about it. And one more word about the Hamburg community involvement in the OPSAT mission. This was the last days of OPSAT in May 2024. So at the very end of the mission, the operational team decided to just leave the UHF radio transmitting all the time. Usually it would be only transmitting over Darmstadt, so only for a short period of time, probably due to licensing, like you needed an active operator to manage it. But for the end of the mission, they just left it open. Yeah? So when they just knew that the satellite is going to deorbit, the drag on the satellite was so high that it was just dropping altitude. They just left it open, and as you can see, this is the heat map of all the satellite stations that were able to pick up the signal. And here we have a graph of the spin rate. This is the spin rate, but also altitude, I believe, of the satellite. So you could see as the satellite was behaving more hectic, as it was getting lower into orbit, it was rotating faster, and at some point over Pacific, it just went silent. So I believe that was like the 28th of May 2024. So basically, that was the entire OPSAT mission, and and thanks. That's all I have to share about today.